G'day. Thank you. I'll start with introductions. I'm Lochie. I've kind of uncomfortably call myself an arborist, I guess, but not really sure what to call myself most of the time. But I get involved with this, I don't know, some crossover between engineering and trees, and I also do all the boring stuff like impact assessments and trees and development. But I got asked today to talk about, impulse tomography, which most people would call sonic tomography, I guess. And so I very hastily put together something about that. There's some boring stuff at the start about introducing what it is, and then we might get to a point where we'll talk about some of the mistakes that can be made and what to look for. I guess the most important thing I thought for people in this room would be, what do we look for when we get these images? How do we know we've got something that even is somewhere in the realms of reality? And what can we look for in these images that says, hey, I've got a bad image here, or the person I've engaged or myself to do that maybe either hasn't done the best job or hasn't applied the technology correctly. Has everyone in this room seen a sonic tomograph before? You know, nice colour. Everyone's, yeah, that's good. So I'll go next slide. Like, what is a tomograph in general? So the tomograph's the machine. A tomogram is what pops out the other side. It's an image of a cross-section of something. We can actually make tomograms from lots of different things. Mechanical impulses, sound, which is what we're going to be talking today, but there's also electrical current, where we measure voltages across something and build an image that way. Electromagnetic waves, which I've included a photo here. GPR is a really common, or C-scans in GPR are a really common tomogram we see elsewhere. Magnetic resonance, not common in trees, but MRIs is something you might have seen before. X-rays, which there is a machine available on the market, which I've never seen, that can take a tomogram with X-rays, but you need some crazy accreditation and doesn't seem like so much fun. So we're talking about impulse tomography today, where a piece of sound is sent between microphones all around aligned in some way around the trunk, and hopefully we know the distance between those microphones. We're only measuring the time between when we whack one sensor and how fast it gets to all the other sensors. So it's a start and stop, like a time of flight measurement, sometimes you'll hear it called. There's no frequency or magnitude data collected. So all we know is the time, this sensor to this sensor. As far as I know, there's 3 models of impulse tomographs available on the market. A FCOP unit, which Ken mentioned before, they make a tomograph too, which I happen to have. The Arbitom, which is a Rintec, a German unit, and the Picus, which people might be most familiar with. Just brand names, all are the same kit, and the differences are normally in software mostly. So they're all, for all intents and purposes, the microphones are similarly sensitive. You don't need to worry about the kit too much. It's what happens under the hood, I guess, in software and the interpretation of the data, which matters the most. Well, I guess, why do we want to do it? In most cases, we want to assess the structure of the trunk, or the large branches, somewhat non-destructively. I have a question mark over non-destructively there. I think it's kind of sold us to arborists in our initial training that this is the gold standard. We don't harm the tree in any way, but we're still banging nails into the tree. And personally, I have a hunch it's probably close to as destructive as doing resistance drilling or something like that. It's similar sized holes that go into the wood. You're introducing air. It's not perfectly non-destructive, but currently it's about the best we've got. So I've just got some more questions here, which we might try and answer through this little chat. Is it scientific? There's a good, little doctrine that says, I heard the other day that said, all science is measurement, but not all measurements is science. And I think sonic tomography fits really well in that. It's not a particularly scientific piece of kit, in my opinion. We don't have a way to control variables very, very well. And for that reason, it's very hard to repeat. If you take one measurement and come back the next year, it's very, very difficult to repeat a measurement and get a similar image. There's always some variability. And that variability and repeatability depends on so many variables that are very hard to narrow down. Is it accurate? That's, unless you have the control, we don't know. So that's an interesting question too. And is it a bit of an art and a science? And I say yes, because it's still largely determined by the technician who's operating the piece of kit. Like, if you gave 5 people acoustic tomographs and asked them to do the same tree, you'd get 5 different images back. And as you train them more and more, you'd get in even more. The images would vary even further. So there's a lot of variables here that need controlling. So the base theory comes down to, as we assume that the tree is homogeneous, which we know they're not. So this is first variable that we can't really control. There's, we have rays, we have reaction wood, that's all of different densities and stiffness throughout the tree. But currently, for the purpose of sonic tomography, we assume that they're the same, for the most part anyway. And we say between the sensors, how fast that impulse is going to travel is dependent on how stiff the wood is, divided by how dense the wood is. Now, and that's and then we take the square root of that to get the velocity, and that's the base theory. It's the speed of sound through a solid, same formula, I guess. And I've got a base, like, if your stiffness and your density decline at the same or similar rate, what happens to your velocity under that proviso? It stays the same. So thinking about it, if you had wood that declined in stiffness and density at the same time, what would happen? We wouldn't be able to detect it. It would be the same velocity through that path. So we'll touch on that later. I'll come back to that one. So we go out, we collect them. You might have seen it. We're going to do one later. I'm going to set it up on a beach, hopefully, if it isn't raining, over in the Bock Gardens, and everyone can come and take a tap, have a look at the data. But we set up the microphones around the tree. We measure between them with a big, weird caliper. Some other pieces of kit use a tape measure to kind of infer where they are. Bit of a different process. I don't like that as much. I use a caliper so I know with a bit more certainty where each one of the microphones is. It's very, if you're relying on a meters per second, so this is what we get meters per second out of the machine when we whack between the sensors. If you're relying on a meters per second between the sensors, you need to know quite accurately where the sensors are to know how many meters you've gone in however much time. So we get all these times, it records them into this matrix, and then we compare them against each other, basically, and then say, we only have data for where all the lines cross, right? So all the little bits between where nothing crosses, we just interpolate, which basically means make up what that data is from the closest points. And normally in all the software, that's done with a process called inverse distance weighting. I just chuck that in there because it's a biomechanics day and I thought we should say some fancy words. But basically it just says how far am I away from the next point, and it scales the data we don't have proportionally from that. So we get all this machine and we get all that data, and then it plots it onto an image. So it's reconstructed in some way and we put it onto some kind of colour space. So all the software, you can pick different ones, but typically it might be, green, orange, red, and we get this limited amount of colours to put the image in to say, hey, these certain, it might be the top 25% of times get put in that their sound wood, the bottom 25% of decay, and in the middle we have to sort them in some way. So it makes an image into that, and also in that the machine has to figure out what are we going to consider sound wood and unsound wood, and we might call that decay typically in trees, but we don't know. So we have to sort that out of all this statistical analysis of the data, I guess. An important note here, and perhaps people won't get this straight away, but I hope it comes later in this, is that if going back to stiffness and density, if you're going from sensor 6 to sensor 10, you're going tangentially across the tree around the outside, and you have to go through rays which are denser and stiffer. So those times seem to be a lot slower. So all the software out there basically corrects those ones that go around the outside, these times. I'll go back to here, but all these ones that go around the outside, it applies just a static value based on the species of what it thinks, hey, these ones will be, typically it's like 0.8, so 20% slower than the ones that go through the middle. But it's a problem because that's rarely, we don't know that actual value. It could be 40% slower, and trees like a ginkgo, I've measured them as like 60% slower around the edges, really strong rays. Some conifers are a lot like that, but so we don't really know. It's just a guess by the software. So you're I guess, implementing noise into the system always when you use these static values, and it's a bit of a problem. But so we reconstruct our image, and I mean it's problematic. Unfortunately, the projector kind of doesn't make the colours look right here. But if you get all these times and put them on a scatter plot, you want to categorise all your data over as narrow range as possible, because you have to put all of it in a box, right? And you get, say, 4 colours. You get red, yellow, green. So we want to know over as narrow a range as possible where to put each piece of data into what box. Now, if we've got these uncertain tangential times, or perhaps you leave a tape on the tree, you can get these really slow and really fast measurements, which make you categorise the data over a really large range. And so you get all these, these sort of data points that are the yellow, like not red, not green. They're uncertainty in the middle, when that's not what they are. They're actually the data that's being collected correctly, but the machine's categorising them, and often in decay. So that's an issue. So all the machines in the box, you have to do a statistical analysis on the data and tell the machine and the software how to sort your data points so it avoids the scales them and puts them into the colour space and categories over as narrow a range as possible. And for example, it can matter, that statistical analysis can matter a great deal. This is a tomograph we took in a Eucalyptus monifera. Ben and I, who's in the room, took this one 4 years ago when I had no idea what I was doing with the machine. We just bought it and thought we were the best arborists in the world, and then had to learn all this stuff later. But you'll notice at the top it has loads of this yellow, like kind of around the outside. Unfortunately, it's a little hard to see on the projector, where this one is a nice solid pocket of green all around the outside, red in the middle. And that was the differences in these images is nothing to do with taking the tomogram. It's just purely categorising the data in the software and scaling it, and makes a big difference. And we'll get into what strength loss is towards the end, but 22% strength loss on the top and 8% strength loss on the bottom. So it's probably the top one. You might be thinking about some mitigation. Some people would, depending on what threshold they're using. We'll talk about that later. And the one on the bottom would be perfectly fine. And there's no difference between the measurements, just how we've categorised the data here. So it's a big difference. I think I put these in because I wanted to let people know what to look for if they get tomograms. If you're sitting in a council office or someone puts something ahead of you, is avoid, if you see large swathes of decay or unsound wood on the edges of the tomogram, and you're like, well, hang on, I see wood there. That's the biggest sign that you've got a bad tomogram. Something hasn't been done right, because it's these tangential, these slow speeds around the edges that haven't been corrected properly in the software. And the operator probably needs to go back and categorise that data in a way. So the other thing, and I said this to, when you're getting going, a massive thing that helped me is I was getting results which weren't consistent with a resistance drill. That's very, very handy, a resistance drill, because it doesn't lie as much as a tomograph. It gives you really very, very good control for this process. So I like it a lot. But some people don't like you drilling trees. That's fine, but I think it's probably not so destructive. The other thing you might see sometimes is like a cheese grater pattern. So like what looks like a cheese grater on the tomograph. And that's typically when you've gone through bark And it's very difficult because thinking about that density and stiffness, bark in the middle of the tree is not dense. Then the sensors only capture it in one direction. So you'll end up with this kind of crisscross, crochet pattern across the tomograph because it's half of the measurements are being obstructed by the bark, the very, very slow measurements in the bark. So they're two big things to look out for. The other one is, like I said, shit geometries that don't look anything like a real tree. Like the distance between the sensors is really important. And some of the manufacturers will tell you it isn't, they're lying to you. That's not right. They're just doing that to sell machines because they say them as easier. So you have to know, you need to have a tomogram that reflects the cross-section of the tree. That's critical. I put more bewares here. These are two tomographs, same measurement on the same tree, just processing. This one, I think Ben and I did it again. This is another one 4 years ago, but we left the tape on the tree. And sometimes when you were measuring where the sensors are, kind of, and sometimes those impulses can go really quickly through the tape between sensors. So you need to rule them out too. So yeah, this is a massive difference, 19% on the bottom and 61% on the top. And you'd be thinking about, most people I would think about removal on the top straight away. This is a bad tree. It didn't look great either. On the bottom, you'd probably be thinking you'd do nothing with some thresholds. So it's a big difference between not doing anything different but some statistical analysis. So you've got to, beware of that when you get tomograms and you're sitting there looking at them. Particularly around the edges, if you see these big swathes of decay, something's not right. I caught this one. This one was in the public domain. Many of you might have seen it. It was the Warburton tree that came down. A couple of contractors had a crack at this one. And I'm not saying that they're wrong, but they probably didn't do the best job because there's a big split in the middle of the tree here, which is not dense. In the middle, it's air. It's, several thousand times less dense than wood. So we're getting these really slow transmissions through the centre of the tree, and it's showing as decay, but really that's a split in the middle of the tree. And I think this tree, at the end of the day, part of the reason, at least to the community, was that it was removed through just, at least partly due to being decayed, when it probably wasn't, it was just split in the middle of the tree, or not substantially decayed anyway, not to that extent. So there was some problems here, and a lot of that could have, when you do get splits in trees, if you look at the stats and you have a look at a scatter plot of the points you've collected, it's very clear that you can deal with this in software, at least partly, and get towards a more accurate representation. I'll go back to this. Another interesting thing about this is I took a bit of a keen interest in this tree. It's hard to find the different reports now. They've been removed from the council website, but I found one. And another contractor had another go, and the different kit got a cheese grater pattern where it's through bark. So it had one of these funny tomographs where you saw this kind of like grater, crochet pattern across there, which sort of says, I look at that and go, I think that's not particularly accurate of what's going on. It's more reflecting that we've got a split in the tree, which still very well may have needed to be addressed and possibly removed. I don't know. I still think before we allow the removal of a tree, particularly a prominent tree, we should ask for some kind of control to tomographs because it's not particularly scientific. Resistance drilling is great. I want to do that as much as I can on trees, but particularly when they're a little suspect. Like I just overlapped some, scaled them and overlapped them. And it was interesting that on this tree, there was actually a piece of bark, a little piece of wood that came right around the outside. It was only very small, and you can see a little bump here on the resistance drill. So the resistance drill picked it up. I could not get it to show on a tomograph. It was just too thin and the nail of the tomograph was going through that piece of wood. So I think if you're at all suspect on the tomograph, ask for increment borer works well. I've got some colleagues that use those. Resistance drills, pretty good too. But yeah, ask something that we can control the data with, that we can get a more firm solution, I guess. Now, I come back at the start, start saying what happens if the stiffness and the density of the wood decreases at the same rate. I've done a bit of work on I have a feeling most people would call it Phellinus robustus, but new information is we don't know what it is. Phellinus robustus is a conch of oak in Sweden, never been recorded, hasn't been here, mislabelled in books for a really long time. So the correct thing to call it is Hymenocetaceae, and it's a simultaneous white rot. So it brings down the stiffness, cellulose, and density, lignin, at roughly the same rate early on in the process. So it's really hard to identify with a sonic tomograph. You can kind of see I got the very edges of it here. Along the edge, there was some sort of visible decay right on the outside. I suspect some sapwood, but in those cases, and you suspect you've got an infection of that, sometimes this sonic tomography isn't the most suitable piece of kit, and I had to move to an electrical resistance tomograph, which they're very hard to interpret, but around the outside here we can see kind of this whole area here would be showing it as green if it matched the tomograph, but we're showing this large sort of amount of sapwood dysfunction on the outsides there. So yeah, just to know that we can't identify everything with it too. In Europe, they're very interested in identifying Kretschmeria. You might have heard of that. I think it's black cinder fungus. And it's a soft rot, and it does a very similar thing. And currently, they're scratching their heads on how they identify that in trees and figure out the extent of decay. It's very, very tricky, typically in lime trees. And I think just recently they found it in Queensland. I had a colleague talk about finding it up there. So, well, the next question is, once you get one of these tomograph images, what do you do with it? And that is a tricky one, and kind of, it's good that Ken was here earlier because we still have no absolute firm solution, but there's some good ways, and I think you've got to implement one, and ideally you get further down this list. So you can go and have a look at the image and do what's called wet finger analysis, but the problem with that is the structural properties of the cross-section we're measuring are dependent on an exponential relationship, and humans are typically really bad at looking at those. So and I see it all the time. Sometimes I get on social media and you'll find a cross-section of a tree and go, this one was so hazardous it needed to come out. And having done this for a while now, I look at it and go, that tree was, or at least in terms of trunk fracture, was very stable. So it's a very hard thing to look at. Even with experience, I'm not good at it. And we'll talk about what that is later. There's thematic shell wall ratios, so the T over R, TR ratios, 1/3, and their derivatives. That perhaps a little bit better, but I think it should just be a starting point. If you get to the 1/3, that's when you should just be interested in doing a more in-depth analysis. So I think that's a good place to say. Anything under that's fairly unlikely to fail due to bending stress anyway. So in trees, and that's been fairly well ascertained in the literature. Then you can take the next step, which is to analyse as a structural member. And people typically do that as a slender beam. Treat the tree as a beam and apply engineering formulas in some way. This is what I do, and it's interesting. It's very non-perfect, mostly for the reasons that Ken was just experiencing. To categorise a load on a tree, currently we have to use drag coefficients and all these things which are super imperfect, and they don't consider dynamics at all, or periodic effects over time. So it's not perfect, but it's probably the best we've got. And I put a little future thing about maybe where it goes, and you might not recognise Bayesian inference, but that's what all these LLM models are doing. They're using this statistical formula to update a token or predict what the next token is. And I think we can feed information into an AI model that asks questions, and maybe it can categorise dampening based on the structure of the tree in some way. We don't have to be perfect. We can ask these very vague questions and supply more vague information to narrow down on, stable, unstable, critical, and perhaps get there. And there's a little bit of efforts on there. A guy called Philip Trelay did a little talk on it at the UK ARB conference last year, and I was really impressed by it. And yeah, I want to do some more work in that space. And fuzzy logic, something a little similar. you might see it on your washing machine. Sometimes washing machines use this statistical treatment to figure out like when the load's done. And we could do a similar thing by asking questions, these fuzzy questions, and narrowing in on a non-fuzzy answer. I think that's maybe the future of where we go with this kind of thing. How are we going for time, Shane? Yeah, we're okay. Okay, so I'll talk about where we go. We talk about assessing this tomograph as considering the tree as a slender beam, and we unfortunately have to do that with treating the tree as a solid, this lollipop pretty much that just bends when the wind hits it, which is not right. But really what we're trying to do is analyse how the system, the tree, deals with an energy input, which is usually a bending moment introduced through wind. I've talked about this. The current methods are problematic because they don't consider periodic effects over time. They're all static. We look at the tree once from a static point of view. They're not dynamic, and those inertial factors we don't consider. They don't consider any branches, which is problematic. All of them rely on calculating the second moment of area, which is that exponential relationship I told you about, but we'll go to that. This is the beach, which we're going to look at later. I come a few weeks ago and took a tomograph of that beach, and I took this. So the blue's the sound wood, and the white is where I think is hollow or decayed, non-intact wood that we consider to have zero strength. Now, the second moment of area is a kind of sum of what the rotational inertia of this cross-section is. How well does it resist being bent? And this is kind of the red line that you see there is kind of like a backwards diagram. This tree would resist bending the worst where the red circle is the largest in diameter, if that makes sense. And this second moment of area is calculated each little square that gets away from what's called the neutral axis, which is where there's no compression or tension, where the tree's pivoting around, gets the square of its distance to that neutral axis. So say this little square, if it was 10 away, would be to a magnitude higher, rotational inertia, or this second moment of area contribution to the ones closer to the neutral axis. But it might not mean much, and I probably haven't done a good job by there, but it's not intuitive to calculate, and we really need computers to have a look at it. And a good example is this one to the left, which is a Frank Rinn diagram. Those two shapes have the same rotational inertia, this second moment of area. So even though the one on the right is, two-thirds more hollow, they're of the same strength as far as this is concerned. So, and I put this sort of little graph I plotted in an online tool to sort of show how it increases, of how critical these outside fibres contribute to this second moment of area. These outside fibres are so much more critical. Something here is at 200, where something just in here might be at 10 of its contribution to how strong the cross-section is. So all of them use this kind of term, I guess, to calculate how strong this cross-section might resist a certain load that comes down the tree. They take it a step further. I only put this in here. You might hear it referred to as section modulus sometimes. It's this second moment of area. The section modulus is that second moment of area divided by the distance to the neutral axis. But basically, it just combines the geometry of the tree and the second moment of area in one nice number. This number is what's called loss in load carrying capacity in the arbitom. You might get something on your desk that says, hey, we've lost 6% of our strength, and that's really a loss in 6% of section modulus. And it just means how well does this cross-section resist bending, basically. And that's what they all work out. The tomographs, they put this image into a computer and spit out a section modulus, basically. So we get all that, and we say how much loss of that section modulus